So I told already, I tried to interpret that one already. Suppose if you have a light source here, and if you held, so this is the area, okay. Suppose take light source, light rays are your field line, isn't it? Light rays will also behave in the same manner, am I right? So just like, so you have a point charge, electric field will diverge from the point charge, am I right? So similarly, if you have a small point light source, your light rays are going to diverge, isn't it? So now, yeah, so can you see any simulations? Yeah, let me share it later. Okay, let me share it later. So there are a lot of simulations on that one. You can see. So one is, yeah, I have a light source here. You can see its shadow. Am I right? Whenever I put one light source here, you can see its shadow below. That shadow talks about, I mean, those light rays are obstructed by the area, isn't it? If there is minimum shadow, that means not much light rays are obstructed by the area. If there is maximum shadow, then obviously light rays are piercing this area. That's why, again, it is not passing through that area. That's why you have a large shadow, isn't it? So now look at here. So number of light, if I put a point light source here, number of light rays passing through this surface area. So that is one thing, is that should be proportional to this area, isn't it? Let me take one planar area. Let me take a vector field. Okay, let me take vector field, and let me take one plane area. So one plane. Is that okay? So now number of vector field line passing through this this area, planar area. Let me take planar area. Okay. And one more thing I have to take here. Yeah. So let me just see. One more thing I have to take here is, idea is, our field lines are almost constant. Okay. If they are not constant, you can't add up. Am I right? So if they are variable throughout the region of that plane, then what you have to do, you have to integrate actually, isn't it? To find total flux. For a time sake, let me assume I have a uniform vector field, any vector field. Electric field is our discussion, and I have a what you call planar area. So now, when I have a source here, so your light rays will fall on this one. Number of light rays passing through this one, that is proportional to, I can't count that one, isn't it? Number of light rays. I can only talk about proportionality. Number of light rays passing through this one, that should be proportional to area, obviously. Am I right? If you increase the area, number of light rays will increase. Am I right? Number of light rays is proportional to area. So we call it as flux. Is that okay? That proportionality factor, we call it as flux. Flux is proportional to area. Okay, magnitude of the area. So later we are going to construct area as a vector, isn't it? Later we are going to construct area as a vector. And that is also proportional to, remember, I told one idea, whenever field strength is more, you have to draw more number of field lines, isn't it? That's one of the way. So suppose here, if I have charge Q, you may draw field line like this. If you have a charge 2Q, you have to draw still more field lines. Not only in this direction, in all directions. Are you getting my idea? So if charge is increased, obviously field strength is increased. Am I right? How do you show that increase in the field strength? By increasing number of field lines, by increasing density of the field lines. Is that okay? So that's how you have to show. Now obviously, so when you increase the strength of the field, what would happen? So suppose if you are increasing the intensity of this light source, suppose if you are talking about, then more number of light rays are going to pass through this one, and obviously then also flux is what you call more. Am I right? That's why flux is proportional to, let me take electric field as my vector field, magnitude of that one also, isn't it? Not only that, yeah, it is proportional to magnitude of the vector field. Magnitude of the vector field will talk about how many lines are there, okay? What is the density of the field line? Is that okay? If magnitude is more, density of field line is more, so more number of field lines are passing through that one. What we are having here, flux is proportional to, so flux is a measure of how many field lines passing through this area. Is that okay? That depends on magnitude, obviously, because magnitude will decide number of field line. Is that okay? So now area, obviously if area increased, it will increase. Not only that, some cos of the angle between them. Now I have to define theta, because look at here, I have same area, same strength of the field or light rays here, okay, but it depends on the area, am I right? So suppose if I held it like this, you will have a maximum shadow here, isn't it? If I held it like this, I have a light source here, you will not have any shadow. That means your light rays are not puncturing this one, isn't it? So that's why it should depend on some relative angle, am I right? Now our idea is to construct one vector perpendicular to the area, okay? Now you have to ask one question, okay? So I mean that's what we call that one as area vector, am I right? Area vector, it is always perpendicular to the area. Now if I take this is planar area, so now area vector will be like this, okay? Area vector will be like this. Suppose if I held it like this, so now my chalk piece direction, it's a area vector direction. Now light rays will also point in the same direction, cos 0, 1, maximum flux, isn't it? So when I had this one like this, look at here, your area vector which is perpendicular to the surface of the area, so which is perpendicular to light rays. So if my point source here, is that okay? So then your flux is 0, isn't it? Cos 90. So now this the relative angle between this area vector and the vector field. What is area vector now? So I mean that's our construction, remember. So to define this thing, to explain this nature, it's our construction. It's a imaginary area vector. So it's an imaginary vector, so which is perpendicular to surface, whose magnitude is area itself. Area vector is an imaginary vector perpendicular to the surface, whose magnitude is area itself. Is that okay? So now cos theta does matter, am I right? Suppose if you held this one, what you call like this, suppose if you are holding your plane like this, am I right? With area vector like this, and your electric field is like this. Is that okay? Then what would happen? Electric field lines are grazing that one, they are not piercing into that one, into that area, isn't it? So that would happen. In that case, again, theta equal to 90 degree, your flux equal to 0, number of field line passing through the area equal to 0. So now, so combiningly, what I can write now? I mean, so we will not take any proportionality constant, we will make it equal. So actually I have to write flux equal to this one, okay? Actually I have to write flux equal to this one. Then I have to quote that this is proportional to number of field line passing through the area. Is that okay? This is proportional to number of field line, so passing through the area, like that. Is that okay? Now look at here. So how do you write now here? E dot area vector for a planar area for a uniform, so what you call field. So now suppose again let me take other situation. The situation is, suppose electric field may be varying or area, so area may be a kind of curved one like that, okay? Let me take that situation. I have a curved surface area, is that okay? And my vector field is varying, okay? It's not uniform vector field, its strength is also varying, is that okay? And its directions are also varying, is that okay? Let me take like that. Now I have to find flux of that kind of vector field line through some curved surface area. Then what will you do? So you have to do surface integral. To before going into surface integral, what would you assume? You have to take one elementary surface area. You have to take one elementary surface area. Obviously, your area vector, I call this one as dA vector. I call this one as dA vector. Okay, that's always perpendicular to that small patch of area. Am I right? So then maybe, so it at this point your electric field will be in this direction. At that point, okay, at that point. Now take the dot product between electric field and that small area vector. What will happen? That the flux through that small area vector, isn't it? Flux through that small area vector. So that is, I can call it as d phi, small amount of flux through the small area. So total flux, so through the surface, so I mean over the surface, our total flux, flux of field line passing through the surface, That's nothing but surface integral of, we call this one as surface integral, E bar dot dA bar. Is that okay? Now, throughout the surface, so look at here, electric field strength may change. Electric field and dA vector, this angle may change. So, everything should be taken into account, isn't it? Earlier, what I have taken? So, I have taken uniform vector field. That's why it was very easy to calculate the flux. Is that okay? So, if you have a planar area, if you have a uniform field, then you can just use this one. Am I right? So, but if you have a non-uniform surface area and non-uniform field, then you have to go for surface integral. We call this one as surface integral. And that's a scalar. The result is a scalar. Can you just write one more sentence here? E dot dA is proportional to E dot dA is proportional to the number of lines passing through dA vector. We said proportional. Why? We can't count exactly. Is that okay? We can't count exactly, isn't it? It all left to our choice. Remember, electric field is a kind of that's our choice, isn't it? Now, just read out Griffith's all of his comments. Okay. Yeah, now let me slowly get into Gauss law. So later I'll give some more arguments. Okay, so now let me do in in this way. Later let me argue. So this is the definition of flux. Okay. So whenever you have a flux, so through some surface, you better write E dot dA. Okay. Suppose E vector and dA vector have got same angle. The angle between E vector and dA vector is same. Then what would happen? I can write this one as mod dA cos of the angle. Am I right? Suppose throughout the surface, electric field is same, angle between them is same. You can take both of them outside, isn't it? Suppose my first example. I can take electric field as well as cos theta outside. Integral of dA vector. What is this one? Integral of dA vector? That's a total area, isn't it? That's the total area. That's what your earlier formula. Is that okay? So that's how it works for a special case. But that is the most general equation. This is the flux through the surfaces. You have to read like that. Okay. You better to put S here, capital S here. Remember, sometimes we are going to use this one, not sometimes. Now, let me take that example. So, E bar dot dA bar, what is the difference between these two? This should be closed surface area. Is that okay? For closed surface area, you have to put one more circle here. Okay? For open surface area, you have to leave it as it is. Okay? That is the accepted notation. So, don't make any mistake. If surface is open, don't unnecessarily so encircle that one. If surface is closed, don't forget to do like that. Okay, be careful. Closed surface area. Suppose a spherical surface, closed surface area. Is that okay? Open surface area. Example, suppose your ice cream cone. That's an open surface area. Am I right? It's open one side. Suppose a hemispherical bowl. So that's also open surface area. Am I right? So here one problem comes. In case of open surface area, suppose if I take let me take hemispherical bowl, open surface area. Am I right? So now what is the direction of dA that you have to choose? or any surface. Look at here, you have a surface here. So you got two perpendicular direction, in which direction you have to choose area vector? Direction? Why? What the logic? What the logic to choose? I mean, if it is not along the field, then what will you choose? Are you getting my point? I have a vector field here, uniform vector field. Let me take that idea. Okay, I have a so planar area here. Okay, now I got two choice. One is this direction, other is this direction. Am I right? I got two choice of defining area vector. Which one you are going to choose? One, I mean, so now this this vector and this electric field vector, the angle is more than 90 degrees. Am I right? This vector, this area vector, and this electric field angle is so one is acute angle, other one is obtuse angle. Am I right? So this will give negative flux, this will give positive flux. Are you getting my point? Cos of obtuse angle, I think that's less than 1. Am I right? Sorry, negative, isn't it? So this area vector. So I mean, so electric field and this area vector, this has got obtuse angle, isn't it? This has got acute angle. Then obviously, if you choose like this, you will get positive flux. If you choose like this, you will get negative flux. But it doesn't matter, isn't it? Number of field line that we are trying to count, it doesn't matter actually. Is that okay? But when you connect this one to the theorem, I think Stokes theorem or Gauss theorem, that convention will come. You have to choose your area vector property. Is that okay? Right now, we don't have any convention. For open surface, we don't have any convention. Is that okay? To choose this dA vector, you can choose either. Look at here. So in case of this hemispherical ball, you can choose your dA vector like this, or you can choose your dA vector inward. Isn't it? You got two choice. You can choose in any way. So if you choose in one way, you may get a total flux positive. If you choose in other way, you may get total flux negative. It doesn't matter. Magnitude will be same. Okay, magnitude will be same. So that's why whenever we write that open surface integral, that ambiguity remains. How to choose your area vector, dA vector. Okay, that ambiguity remains. Okay. So, but when you connect that one to theorem, I think which theorem? Stokes theorem, isn't it? When you connect that one to Stokes theorem, there the let me just discuss that one. The convention comes. Okay, then you have to follow the convention. Look at here. But if I have closed surface area, okay, I don't have to take sphere, isn't it? So it is very conventional again. Okay, it's very conventional. We don't have logic over it. Okay, that to choose your area vector, dA vector outward from the volume. So one closed surface will produce one volume. Am I right? Inside that one, there will be one region, isn't it? So closed surface always defines one region, one volume, isn't it? So now it is a convention that to choose your area vector outward from that volume, isn't it? It can be of any shape. Remember, it is always convention to choose that area vector outward from the region. Okay, so I mean wherever it is that area vector, you have to choose this one dA vector outward from that region. So again, you have to ask question why we have chosen that convention. Okay, so now that is to make outward flux positive, inward flux negative. Look at here. Let me take the simplest example. Suppose I have a charge Q here, plus Q here. Okay. Now obviously, electric field lines are going like this. Am I right? Now if you just take a dA vector, if you take dot product with electric field, what would you get? That's acute angle. You will get positive. So the same thing will happen throughout the surface, and you are adding all of those positive quantities, you are getting net flux positive, isn't it? Suppose if you have chosen your area vector inward to that region, what would happen? Look at here. This is suppose if electric field is like this, dA vector like this, then it's 180 degree or obtuse angle. It not need to be 180 degree, remember, obtuse angle. Then look at here, negative flux. So when you integrate throughout the region, so I mean throughout the surface, you will get net negative flux. Am I right? So our idea is to make outward flux positive, inward flux negative. To make outward flux positive, you have to choose your area vector outward from that region. You can just think over it. Just draw that one and think over it. To make outward flux. When you talk about outward flux, wait a second. Only for closed surface. For an open surface, outward flux is meaningless. Am I right? I have one out. I mean, suppose I have some electric field lines here or some field line, isn't it? For an open surface, outward flux doesn't have any meaning, isn't it? Because open surface will not define any region, isn't it? So which is outward, which is inward? You may feel like it is inward, am I right? Just go here. This is outward, isn't it? When it passes through that one, it is outward, isn't it? Or so let me call this one inward. So everything will be confusing, isn't it? For open surface, inward flux or outward flux, it is meaningless. Only flux. Okay, and you better talk about magnitude, because again ambiguity comes. How to choose dA vector, isn't it? dA vector either this direction or this direction. That's why for open surface we can't define inward flux or outward flux. That's meaningless. Or so this is a curved one. You may have some confusion. Suppose if you have a planar surface here, that's also open surface. Am I right? Now inward flux, outward flux is meaningless. Only flux is flux through that area. Only that has a meaning, isn't it? So, but when you talk about closed surface area, now outward flux means net field line going out from that region. Okay, because that closed surface area will define one region in, it will define one volume. Am I right? In a space. So that's why. So field line, which I mean, if there are net outgoing field line, I mean how to say. So if field lines are going outward from that region, we can say outward flux, because I mean so by saying field lines are going outward, and if field lines are going inward to that region, isn't it? We can talk about the region that will be inward flux. Okay. So this idea of choosing your area vector outward from the region of the closed surface is to make outward flux positive, inward flux negative. So write that sentence. So choice of or choosing dA vector, outward from the region of a closed surface, and that dA vector should be perpendicular to that patch. Okay, again for any surface you have two perpendiculars. That is our one is our choice. Am I right? For any patch you got two perpendicular. One is like this, other is inward. Am I right? You heard the sentence? Choosing dA outward from the region of a closed surface. Choosing dA vector outward from the region of a closed surface is to make outward flux positive. You better write net outward flux positive, and net inward flux negative. Okay, suppose if you had, I mean now this is our convention. Now onwards, whenever you have closed surface, you have to take your area vector outward from that region. Okay, suppose if I had negative charge, then what would happen? Isn't it? Now you have a field line which are going into that one. isn't it? Now look at here, your area vector is like this, but your electric field is like this. Then cos 180 degree or cos obtuse angle, you will get negative. When you add, you will get negative flux. The total flux will be negative. Is that okay? Because that is inward flux. Our field lines are going into that region. That's the inward flux. Okay. So that convention is because of that. Yeah. After understanding this, whenever you talk about closed surface, you have to write closed surface integral of E bar dot dA bar. You can call it as net flux then, isn't it? Net flux. If that net flux is positive, that is outward one. If that net flux is negative, then that is inward one. Okay, according to our dA vector convention. Okay, now look at here. Now let me first prove Gauss law in an integral form. Then we shall come again. Okay. Now for a time sake, let me assume this electric field line property. Are you getting my point? Let me assume this electric field line property, or even after proving that one, so I can show some electric field line property. Look at it. I can show that one. Yeah, those integral and differential forms are equivalent. So that's why once you prove that one, you can talk about electric field again. Okay. Now let me choose one charge at the origin. Okay. Now here I am going to take a spherical polar coordinate idea. So let me discuss in the vector calculus part. Okay. So since it is second chapter, he discussed already in first chapter. Okay. Let me take some idea, something from the vector calculus. Okay. So let me place Q at the center of the origin. At the origin, isn't it? There is no again center of the origin. Am I right? Now then r prime vector equal to 0. Am I right? So if it is away from the origin, you are going to write origin to that source charge, you are going to write that one as r prime vector. So that's why your italic r vector is equal to r vector, r prime vector is null vector. Am I right? So now if you write electric field, so at any point at a distance r from this one, r from the origin, this is origin itself. So r here, electric field at r is equal to 1 by 4 phi epsilon naught q by r square r cap. That's what you have written. But r is nothing but italic r is nothing but ordinary r, isn't it? So that's why I can write as r square into r cap. What is r cap? This is the direction. R cap. Is that okay? This is the electric field when you place that one at the center of the origin. I hope you remember something from that geometry that we have taken in case of classical mechanics. Am I right? So according to our spherical polar coordinate, this is our r cap direction. How do you define theta cap? You have to define theta here. So this will be theta cap, and then you have to take projection on xy plane. Then you can take phi cap. Am I right? So I talked about that coordinate geometry. Otherwise, so just go through that one. Okay. Again, so we shall again discuss this one. Okay. Here again. So in case of our vector calculus. Now what I do here is to make it very simple. To make it very simple, I am going to take one spherical surface. I am going to take one spherical surface. That's imaginary surface. Okay. That's imaginary surface. So whose radius is r itself. Okay, small r itself, which centered at q. Which centered at q. Okay, closed spherical surface. Is that okay? Closed spherical surface with q at its center. Is that clear? And I am going to take closed surface integral of electric field over that closed spherical surface. Now look at that spherical surface. On that spherical surface, wherever you take, if you draw your dA vector, look at here, the dA vector and your r cap are along the same direction. Are you getting my idea? So you have to imagine one closed spherical surface with Q at its center, then if you want to do surface integral of the electric field, that means I am trying to find total flux through that closed surface, total electric flux through that closed surface, then what would happen? So at each point on that closed surface, your dA vector and your radial vector, okay, both are in the same direction. Is that okay? So that's why can I write a dA vector as, dA into mod dA into r cap? Isn't it? Because wherever you take, your dA vector is along the radially outward direction. Radially outward direction, that's the best sentence, isn't it? Radially outward direction, that is r cap direction. So obviously your electric field is also r cap. Look at that, isn't it? So now look at here. So now let me do this surface integral. That is my net flux. Am I right? Net flux through the closed surface area. Don't forget this one. Why? This is closed surface integral. Is that okay? According to our idea, we have chosen our dA vector outward from the region. Again, that was the convention. Look at here. So now if I substitute this, what would happen here? E r cap dot product with mod dA r cap, isn't it? So that is obviously r cap dot r cap 1. So now look at here, mod of the electric field. What is this one? 1 by 4 phi epsilon naught q by r square, isn't it? Now since over this surface, over this spherical surface, your radial distance is constant, r, I have taken r. Over this surface, your radial distance is constant. That's why this is also constant throughout this integral. How this integral runs? This integral runs throughout the surface area, isn't it? So now throughout that surface area, this mod E is constant. I can take that one outside, mod E. Am I right? So again, so when you take dot product, that becomes mod E into mod dA. Or you don't have to think about this r cap, you can just think about mod E mod dA cos theta. So theta equal to 0. Look at here, everywhere the angle between dA and electric field is 0. You can write like that also, but I prefer coordinate geometry, okay, most general, okay. Now look at here. So mod E is constant, your electric field magnitude is constant throughout this surface, am I right? Obviously, each and every point is at the same distance from the charge, isn't it? So that's why this becomes integral of dA, mod of dA throughout the surface. That means you have taken small area, you have added throughout the surface. What you are getting? You should get total surface area. That's it. That's why that's equal to mod E into what is the total surface area of this surface? 4 phi r square. Just multiply with mod E, what would you get? 1 by 4 phi epsilon naught q by r square, 4 phi r square, that's equal to q by epsilon naught. What did you prove? Total flux through that surface area, through the what do you call closed surface area and spherical surface area, that's equal to q by epsilon naught, isn't it? Now our idea is to generalize this one. To generalize this one, again you need electric field property. Now I am going to say, if you deform this surface, then also net flux should be same. Why? We have taken one idea. Electric field will start from the charge. It will, if there is no other charge, it should end at infinity. Electric field will not terminate at mid-edge. Am I right? So then it doesn't matter. Shape of the area, shape of the surface doesn't matter. Here I have taken spherical. Why? I can do this integral, isn't it? I can do this integral very quickly and I can show this one. Now I can generalize this one. So this can be any closed surface area. Why? Flux will be same. What is flux? Number of field lines passing through that one, isn't it? So since field lines are generated by that charge and it are ending at infinity or ending at some negative charge outside, so field lines are not ending at mid-air. Again, that is by divergence. Okay. First we have to choose divergence. Why? Why it will not end at mid-air? Because divergence is 0 everywhere. Is that okay? Divergence is 0 everywhere except at this point, isn't it? So that fact said, again, so we shall show that one little later. Okay, here we are going to accept the property of electric field. What is the property of electric field? It is originating from positive charge. It is ending at infinity. So let me assume there is no other charge. So that's why number of field lines should be independent of the surface area, shape of the surface area, and total surface area, isn't it? Shape. Only thing is it should enclose this one. Am I right? If field lines are starting from this one means, so whatever the shape of the area, it should pierce that area if it is closed area. Are you getting my point? That's why shape doesn't matter. So we are going to generalize this one. Any shaped surface, closed surface, it should be closed surface. If you take this one, E bar dot dA bar, what would happen? Q by epsilon naught. Okay. Surface of any shape, closed surface of any shape which encloses Q, your total flux. What is this one? You better write total flux. So after long time, you will forget that. What is this one? This is total flux. Am I right? So sometimes they will ask question with the flux. So total flux. So through the closed surface area. So E bar dot dA bar is equal to Q by epsilon naught. Now ask the question. If I generalize that one to any shaped surface area which encloses that Q, and origin is our choice. Now, if you change the origin, then also this should be true. Am I right? We are connecting very physical quantities here. One is proportional to number of field line, other is charge, isn't it? Wherever you choose, this should be true, isn't it? Wherever you choose your charge, now I have done this one because I can do this one. It's not doable if I take arbitrary surface area, actually. Is that okay? So now, so what is the statement? That's the Gauss law. Wait a second. Now I have done for only one charge. Is that okay? Now electric field will follow superposition. Yeah, question. Yeah, definitely. Due to outside charges. Let me just define now. Okay, let me just define now. Now, whenever you have many point charges, you can take electric field due to individual and you can add up. Am I right? You can assume electric field due to individual and you can work out. So there is no problem with that one. If you have a charge outside Q, okay, so due to this one, electric field line will come in one. So electric field will pierce from one one point. It will go away from other. If there is any charge outside, electric field due to charge outside, field due to charge outside, it will come from one surface, it will go from other surface, other part of the surface. So this incoming, it will introduce a kind of negative flux. So outgoing, it will introduce a kind of positive flux. Those are equal. Again, it's not ending at midday. On the surface, you can't talk about it. You can't talk about it. Is that okay? If charge, because you can't define electric field, isn't it? If you want to find flux over the surface, you should have defined electric field over the surface. So we just discussed earlier, am I right? Electric field at the point of charge is indeterminate. So that's why you have to avoid that situation on the surface, okay? Outside the surface, I can explain like this. Wait a second, I'll come to that point little bit later, okay? Little bit later. So now what I do here is, I'll have many charges here. Now let me generalize this one like this. Look at here. I'll have many charges. So Q1, Q2, Q3, like that, okay? I have many point charges inside. Okay, now I am going to work out individually. Q1 will produce vector field E1, Q2 will produce vector field E2, like that, isn't it? So now what I can do? I can do like this. So close the surface. This is the surface. Close the surface of E1 bar dot D1 dA. Okay, dA is same. Okay, so plus close the surface integral of E2 bar dot dA. Am I right? So similarly, close the surface integral of. So what I am finding? I am finding flux due to this one, flux due to this one, flux due to this one, because you can take them individually. That's our superposition theorem. Remember. Okay. So now plus close the surface integral of E3 bar dot dA bar. So I mean each of these according to our Gauss law. I mean so according to our individual law. What is this one? Q1 by epsilon naught. So Q2 by epsilon naught. Q3 by epsilon naught. Am I right? One may be positive, other may be negative, isn't it? If that is positive, it will give net outward flux. If it is negative, it will give net inward flux. So now what is the resultant? Q1 plus Q2 plus Q3 by epsilon naught. We call this one as Q enclosed. I am talking about charge inside, okay? Let me talk about charge outside a little later. Q enclosed by epsilon naught. That's our Gauss law. Now look at here, this side, wait a second, look at here. You can do it. It's very easy. Only thing is understanding very first thing whatever I say here. Okay. Now I can take common, isn't it? These are again linear operators. Surface integral is also linear operator, remember. So you can write E1 plus E2 plus E3 dot dA. That's equal to. Now I can generalize this one. What is this one? Net electric field. Am I right? So find net electric field over the surface and surface integrate that one throughout the closed surface. That's equal to Q enclosed by epsilon naught. Okay. So that's why. So net flux through the surface E bar dot dA bar. That's equal to Q enclosed, charge enclosed by epsilon naught. Wait a second, why we are not taking charge outside? Am I right? Again, let me take Q4 outside. Again, our superposition principle says while taking this charge, you can assume there are no effect of these charges. Am I right? That was this superposition principle. What was that? Interaction between any two charges is unaffected by the other, like that, isn't it? Now, so remember. So suppose it is positive charge. Now look at here. Its field will come in one. So its field will go inside this closed surface at one point of the surface, and it will go out from the other point. Okay. Suppose if I take one more example. Okay. Yeah. So shall I rub it out? So suppose let me take one closed surface. I have only one charge here. Okay. Plus Q. There are no other charges inside. Okay, then what would happen? So this will produce electric field like this. What is the net flux now? What is the net flux now? 0. Why? Electric fields are not terminating at mid-air. Am I right? Number of field lines going inside, it should have gone outside, outward from other point of the surface, isn't it? Because it will not terminate at mid-air. That's the idea. Is that okay? That's why. So charges outside the closed surface will not contribute to the flux, isn't it? Charges outside the closed surface will never contribute to the flux. That's why. So that flux is always depending on charge inside. Is that okay? Yeah, speak out. Okay. Okay, this is minus Q. Minus Q, okay. Then also, you are taking minus Q plus Q. Am I right? It's a kind of dipole. Am I right? Like this, isn't it? So then also. Then also number of what you call your flux is same. That's equal to minus Q by epsilon. Wait a second, I did one mistake. What is that one? inward. So from positive to negative, am I right? From positive to negative. Isn't it? Then also it is same. Is it okay? So now look at here, those electric field lines are joined here, isn't it? Now they are joined. So that's why you can't, argue in the earlier way. But that net flux is same as earlier. Just remove this one, then also net flux is same. So these field lines which are ending at this negative charge, it should have either come from positive charge or it should have come from infinity. It doesn't matter. It depends only on the magnitude of this charge. Is that okay? Yeah. Now, charges outside will not contribute to any flux actually. So that's one of the idea. Now, shall I design one question? Yeah, any question? So this is our integral form of Gauss law, okay? Integral form of Gauss law. Now you can try, okay, again I need some coordinate geometry. We now in the next part we better to invest on again vector calculus, okay? We need lot of vector calculus here. You can do problem number 2.10, okay? 10th problem in the second chapter, and that problem is repeated in many exams. Now let me design other question in my way. Okay, I have parallel lines of electric field. Okay, I have parallel lines of electric field. So now let me take, those electric field lines are like this. So let me take, somewhere in some exam they designed this kind of question, okay? I have electric field lines like this, is that okay? So now what I do here is, this electric field, let me write this one as E0 into X cap, that's uniform electric, okay? Now let me take one, a conar closed surface. Conar, that word doesn't exist, I think, isn't it? Cone, closed cone, is that okay? Conical surface. Whenever I say conical surface, you may see, so this is also your ice cream cone, but you are just closing that open surface. Is that okay? Not with the ice cream, okay? Closed surface area, okay? So now this this is radius A. The radius of that base is A. Is that okay? Closed cone, conical surface, closed conical surface, whose base have got radius A. Now this is making an angle 30 degree. This area vector, this is perpendicular to this surface. This is making an angle 30 degree with the electric field. Now what is the flux through the curved surface of that cone? What is the flux through the curved surface of the cone? Draw that one. Draw that one, try to answer. What is the flux through electric field? I am talking about electric field. Now you have to ask, how did I generate this electric field? I have to keep charge at the infinity, isn't it? Or I have to make a big parallel plate capacitor like that. So there are no charges within this one, okay? There are no charges within this one. Now, so get me the flux through curved surface area. Curved surface, this is a planar, am I right? This part is planar surface area. Find me curved surface area, flux through curved surface of the cone. Right. I hope you got what is the curved surface. Suppose if you take ice cream cone, that ice cream cone will have only curved surface, isn't it? Other side open. Base is open usually, isn't it? Find the flux through this surface. write down in a sentence, find the flux through curved surface of the cone. So think over it, okay? Write down and think over it. We better to switch over to vector calculus because we need much more. So to proceed here. And 2.10, that's very frequently asked question, okay? 10th problem. Do all parts. Let me extend those problems later, okay? I have given this area, this radius also, okay? This radius of this base of the cone. Electric field is E0 into x cap. And this area vector of this base and electric field, angle between them is 30 degrees. So try that one. You have to write down, okay? You should not think in the air. You have to think on a paper, isn't it? If you write down, that's nothing. This problem is nothing. Again, use Gauss law. There is no charge inside, okay? Now again, what's the time? It's better to switch over to vector calculus again. Yeah, we got one conclusion earlier. If you have a vector field like r cap by r square, that was this vector field, am I right? I written that electric field. So del dot V is equal to 0 except at r equal to 0, isn't it? We can, because at r equal to 0 you can't take the derivative. That was the idea, am I right? Do you remember? So it gave 0, but if it gives 0, then there should be no divergence at any point in a space. If there is no divergence at any point in a space, how this vector field is generated, isn't it? It is generated by the charge at the origin, am I right? You have seen charge at the origin will give electric field whose vector field is like this, isn't it? So that's why at the origin you should have a non-zero divergence because you have a source over there, isn't it? So divergence, we'll talk about the source. So that's why. So this is 0 except at r equal to 0. Right now we should take that one. Later we are going to use Gauss theorem to fix it, okay? Fix this angle.